Good morning, ladies and gentlemen. 2.1a continued for a little bit here. We left off at example 2, so we're going to do example 2, 3, and 4 quick. And remember yesterday when we were finding limits, you're going to expect it to be finding them algebraically, graphically, and numerically. And if you remember how to find them algebraically, that is simply taking your function above here. What we do is algebraically we substitute in right away. We substitute this target value into the equation, and I get 2 minus 2 over 4 minus 4, which gives me 0 over 0. And 0 over 0, okay, there's a hole. There's a hole in my function. Okay, what does that mean? I think 0, 0 means give it a massage. Keep working harder. Keep working. There is, the is, E-H-E-R. I can't even spell. That's okay. I'm a math guy. Keep working. There is a limit. Exclamation point. That's what 0 over 0 means. It's there. Go find it. So what we do is we take our limit as x approaches 2 of our function. Remember, 0 over 0 means the top and the bottom share a factor. We're going to have to be good factorers. And then if I have anybody tell me, oh, Mr. Crooker, I was never very good at factoring, saddle up, man. Saddle up, because that's going to be a big problem. Okay? And we find out, it's sharing x minus 2. So what happens is that's really looking at the limit as x approaches 2 of 1 over x plus 2. And I algebraically, then I resubstitute it in, and I get 1 over 4. My limit is 1/4. That is my limit. Mr. Kruger, I can't factor. Sir or ma'am, that is going to be a big problem in calculus. The only part of this class that's difficult, and this problem is very basic, is the algebra involved. You will hear me very sarcastically all year saying, we just did our calculus. It's all algebra from here on out. Graphically, how do we find it graphically? Well, please remember, graphically, we need to look at the limit as x approaches 2 from the right side of x minus 2 over x squared minus 4. And we also have to look at the limit as x approaches 2 from the left. This is the right side. This is the left side of x minus 2 over x squared minus 4. And they have to be approaching the exact same number. What if they're not approaching the exact same number, Mr. Kruger? Then the limit doesn't exist. It's not there. When we're doing it graphically, 99% of the time, we will use our calculator, or the graph will be given to us. So if you grabbed your calculator and you typed in your function, okay, it's a nice looking function there. I can see it. We are going to use the trace function on our calculator. And if we want to know when the target value is 2, if I am on the right side, I'm going to say menu, trace graph. If I'm on the right side of 2, remember that's just a little bit bigger than 2, so maybe 2.001. Enter. Oh, I see it, 0.24998. How about 2.00001? Getting closer and closer. Looks like the left side's approaching 1/4, which would be 0.25 as a decimal. That's the right side. How about the left side? Ooh, that would be 1.99. 0.25. How about 1.999999? We're going to get closer than 0.25067. Boom, there it is. It's approaching. So what I can see from here is I can see my limit is approaching 0.25 from the right, 0.25 from the left. That means my limit, okay, and we're going to get into this next week, this, because there's no little subscript up here above the 2, like I have here showing right and left, that means this guy up here in the very top, there's no superscript if that, I don't know what they're called, but if it's not up there, that's a two-sided limit. We will be talking about one-sided and two-sided limits. Therefore, this limit from both sides equals 0.25, okay? Numerically, okay? Graphically, trace. Numerically, table. I'm not going to write all these tables down on my smartboard. We're going to let our calculator find the tables for us. So what I'm going to do is I'm going to grab my little cute calculator back here. And when I do that, I'm just going to hit menu. I think it's Control T for control table. Let me try that once. Escape. Let me get out of here. Let me hit Control T. Control table splits your screen automatically right there. Now, when I'm looking here, also understand I'm only going up by increments of 1 as I'm coming up here. My smartboard is not responding to me. That is not good. So what I need to do is I need to go into my settings. Oh, I know why it's not. No, I don't. So I need to go into my table, edit my table settings. You can change your start, stop. How about we just go into ask for independent variable and hit OK. We're going to come over here, and if we're approaching from the right side, I said we were at what, 2.001 maybe? Enter. How about 2.0001, even closer? And I can see 2.00001, let's get even closer. 2 may be in there, may not. 2. Ooh, 2's not in there. It's not, oh, that's right, Mr. Kruger, it was a hole. How about the other side? 1.99999 or 1.99. I can see I am approaching from this way or from the top. I'm approaching that 0.25 in there. Okay, so I can totally see. I can see it. I can smell it. I know it's there. I can see that graphically it's 0.25. I don't like the fat ones. And properly written, we should really be writing the limit as x approaches 2 of x minus 2 over x squared minus 4 equals 0.25. That's my limit, okay? So we're going to go on to the next one. Notice, the only problemsome areas on this graph that we found out yesterday were 2 or negative 2. Now we're approaching negative 2. Algebraically, we're going to figure this out. I'm going to drag that guy, give me a little bit of room. Algebraically, what we're going to do, we're going to substitute that target value right in there. So limit x approaches negative 2. It's going to give me x minus 2. I could have done this up there. I just wanted to rewrite it just for fun. What we get is we get negative 2 minus 2 over, what would that be? 4 minus 4. That gives us what? Negative 4 over 0. Whoa, what does that happen? A number over 0 is always a vertical asymptote. Okay, so what does that mean? What does that really mean? Because this is undefined in a vertical asymptote way, we're going to see graphically why, but that means the limit, there is no limit. So you can say no limit. See, I'm kind of a lazy person. Most of my professors preferred DNE. That stands for does not exist, okay? Now, oh, but Mr. Kruger, what if we took our simplified version of it, limit as x approach negative 2 of 1 over, what was it, x plus 2? No. Yes, it was x plus 2. And I substitute that in, I get 1 over 0. Ooh, check it out, a number over 0, undefined, okay? Only when it's 0 over 0 does that mean work harder. Undefined, limit does not exist. Vertical asymptote. Graphically, what are we going to do? Graphically, we need to look at it from both sides, okay? Super important we do that. Very important we do that. So we need to look at the limit as x approaches -2, Kruger, -2. I could have used that little skanky. -2 from the right side, that's my right, of x minus 2 over x squared minus 4. That equals, and I need to compare it to the limit as x approaches -2 from the left side of x minus 2 over x squared minus 4. What does that one equal? We're going to pull these from our table. Why does it not exist? Well, let's go take a little look at that. Why does it not exist? So I'm going to say menu. I think I'm going to say menu. I hope I can say menu. Actions. No, table. Let's remove the table. So as we are approaching -2, okay, well, here's where the fun part comes in. Here's my, son of a biscuit. Why is it not working for me? Oh, well, maybe if I pick up this one, it'll work. I doubt it. No, it's not going to work. So as I'm approaching from the right-hand side, the top one, I'm approaching -2 from the right side. That means as I get close to -2, menu, trace graph, that means I'm at -1.99 as I'm coming in. Whoa, I'm at 100. How about -1.999? Boom, 1,000. -1.9999. Boom, 10,000. -1.999999. I'm at a really big number. What is that? 6 zeros. That'd be 1,000,000? Yeah, that'd be 1,000,000. That's pretty good size. Notice it's going up. The limit does not exist, that right side, because I'm not approaching a finite value. To have a limit, you have to approach a specific number or value. Infinity is not. How about, so I'm approaching from the right side, I'm approaching positive infinity, okay? Now I'm going to come back. What am I approaching on the left side? Well, hopefully we can say, how about -2.001? Ooh, it's going down. -2.00001. Boom. That's -100. Oh, what am I approaching on the left side? The left side, come on, baby. The left side, I'm approaching negative infinity. These are not specific numbers or value. Value, therefore, does not exist. If it doesn't exist algebraically, it better not exist graphically. What does that look like numerically? Well, let's grab our table, or let's grab here. Let's do a Control T. If you forget how to split the table, you can do it fast with Control T, or you say menu. How do we do this? We say table number 7, split screen. And of course, I'm going to have to come back in here. I'm going to have to change my settings to ask again because it defaults to auto every time. So if I go to ask, okay, well, if I'm coming in from the right-hand side, I need to come over here and I'm typing in -1.99999. Boom, it's getting really big. -1.9999999. Getting super big. Coming in from the left side. -2.001. Actually, 0.001. And then maybe -2.001. I can see it's going as I get closer to the middle here. In the middle, okay, what's happening is my y values are getting super big and super small or super big negatively. That's what's called asymptotic behavior. Therefore, the limit does not exist. Let's get rid of the table. Now what I'm going to do is I'm going to menu. I'm going to zoom to a number 5, a standard screen, and it brings it right back. And numerically, we got the same thing, okay? How do we find that again? Well, again, it gets super huge. We just push in big numbers for it. The last one we're going to do here, important to see, okay, we're always, when we're doing limits, we are always looking at target values. Whoa, a target value there, infinity? What the heck? How do I do that? That's an end behavior limit. When I am doing end behavior limits, what we are technically doing is we are horizontal asymptote hunting. Okay? We're horizontal asymptote hunting. Algebraically, how in the world would I ever even think about putting in infinity? Well, can I put in a billion? Well, you could. It's not big enough. A trillion still isn't big enough. Infinity's even bigger than that, okay? How do we substitute infinity? We really need to think about it, okay? Got to be abstract, okay? The limit as x goes to infinity of x minus 2 over x squared minus 4. Well, think about this. When we were horizontal asymptote hunting, we were looking for powers of the numerator, powers of the denominator. Okay, think about it. If I plugged in infinity in for that x, if I take 2 away from it, is that 2 doing anything to it? Absolutely not. Same thing, if I put infinity in here and I squared it and I took 4 away, is that really doing anything to it? Absolutely not. So this is why the limit as x approaches infinity, this is why we compare powers. Check it out. Okay, compare powers. Well, now I'm just kind of a simple little fraction. And infinity over infinity, what the heck is that? I don't know, but I think we can all look at this and say, I got a common factor of x top and bottom. So I can reduce that a little bit. Say it goes to infinity, and I'm really looking at 1 over x. Okay, well that makes sense. Well, how do I plug in infinity? Yeah, I'm going to plug in infinity now. I got to get abstract with it. I got to think. 1 over infinity. What does a fraction 1 over super big? What does that equal? That equals super small or 0. Okay? Super small or 0. So my limit, my infinite limit, it's an end behavior limit. I'm looking at my target value there. Okay? I'm comparing my powers. I'm horizontal asymptote hunting, and it goes to, after I compare the powers here, I reduce those powers to here, then I plug in infinity and I think about it, 1 over something super, super big, getting bigger and bigger and bigger, goes to 0. That's why the asymptote's 0 when it's big in the bottom. Well, how are we going to do this graphically? We've done this graphically already, okay? When we do this graphically, we're still going to use the trace feature, okay? We are still going to trace, but in order to go to trace, menu, trace graph, I need to go to big numbers, like maybe 100. That's a really small, 0.0098. Maybe 1,000. 0.00998. Ooh. Whoa, delete. What's happened? Ooh, 9.9. Oh, don't forget about that e to the negative 7. That means take that decimal point right there, move it 7 places to the left, scientific notation. That's super small. The same way as if I needed to know that's my right hand end behavior, my left hand, I could put in negative super duper large, and I can read my ordered pair and say negative 0.00001. That just tells me I'm still negative. I'm underneath 0, but I am approaching 0. If I did it with a table, I'm going to Control T to get my table. I'm still going to come back here, and I got to change this dirty pot liquor to edit table settings to make it ask. Okay, ask me. Then I can go, maybe. Crumb, I got to get over in the X column, though. Maybe 1,000. Maybe 10,000 or a million. I can see, oh boy, it looks like it's 10. Please come over and hover. You should be able to hover or click. Oop, that's scientific notation. You can see it when you put the clicker on it. That decimal goes 4 places to the left. If I was down here at negative, pretty daggone big, looks, ooh, -1? I don't think so. Got to move that decimal 5 places to the left. It's basically 0, but it's underneath 0, okay? So those are, we just put in big numbers and see what we're approaching. You don't have to go that big, though, okay? You can do 10 to 100 to 1,000, and you can kind of see the progression going to 0 before it goes into exponential or scientific notation, okay? So that's what we're doing. Well, bottom line, graphically I did that. We just verified the same way using trace, okay? We're going to look more at end behavior asymptotes or end behavior infinite limits. We're going to look more at those in section 2.2. Little general, whoa, come back. Now when we looked at the domain, okay, this was a rational function. That rational function, the domain of f is all real numbers except 2 and -2. Those were the problem areas for here. Now understand, we just went through here. We found a few limits. The limit exists everywhere on this function. The limit exists everywhere except -2 where that vertical asymptote was. The limit still existed where that hole was. A limit does not find the point does not have to exist for the limit to exist. I just need to be approaching the same value from both sides, okay? With that being said, what I'm going to have you do is quickly grab your notes, turn it to the next section here, and I'm going to knock out part of 2.1 double A, okay? And on your way back, you just might want to grab some toothpicks somewhere out of the kitchen or the bathroom. Prop your eyes open quick as we go. We're going to knock a couple pages off here. Then you'll be able to do a little bit of the homework, not all the homework. Tomorrow or Friday's video will hopefully be shorter than today's and yesterday's. And it's a special limit called the sandwich theorem or the squeeze theorem. And then you'll be able to do them all. But I'll talk to you about that tomorrow. So today, now, we're going to continue into 2.AA. We're going to look at properties of limits. Well, what does that really mean? Properties are virtually the rules that govern limits. This is how we are allowed to use them. These are the operations we do to them. And as I'm looking at all these properties of limits, okay, M, L, C, and K are all real numbers. That means they are constants, okay? Because they're real numbers, they can be whole numbers, they can be positive numbers, negative numbers, decimals, fractions, they can be square roots, they can be irrational numbers. It doesn't matter, they're real numbers, anything that can be plotted on the x-axis, okay? And what I do know about this is the limit as x approaches c of f of x, a function, well, that limit's L, and the limit as x approaches c of a different function, g of x, that one's M. If I know these two limits, okay, I'm going to be able to do the rest of these. Now, the first two limits are kind of, they seem really easy, but they're goofy. People screw these up all the time. The limit as x approaches c of k, remember, k is a constant, equals k. What in the heck? Well, let's come over here. Let me make a little graph for you. And let me just come on here and say, okay, here's my value of c. Okay, that's the x value I'm approaching. And that x value, say it's right here on a graph, okay? And let's say it's constant because k is a constant. That's just a horizontal line at y equals k. what is the limit? The limit of c is what? Well, what's it going to be? It's approaching from the right. It's approaching from the left. What is the limit? Well, this point right here is going to be c comma k, isn't it? So that limit is k. The limit of a constant, is the constant. Okay? The limit of a constant is the constant. Okay? Well, what about the next one? The limit as x approaches c of x equals c. Ooh, baby, this is a good one. That is our identity function. This is the mother of all lines. That is the line y equals x. Y equals x. See my function? My function is x. Okay, well, great. Thanks, Kruger. What does that mean? Well, that means c. If I put a c in there, what comes out is c, right? So this point is c comma c. And what that means is the limit as x approaches c is c. Well, think about it. Let's look at an example just to clarify it. The limit as x approaches 5 of x equals what? Well, when I substitute 5 in, I get 5. Well, if I put a 5 into that identity function, it outputs 5. Okay, so that's quickly what it is. Those are the two that are kind of funky. But how do I get that limit? I substitute that rascal right in, and it outputs my number. Here, I substitute that rascal in, but there's no x to put it in. That's why it only outputs that constant, because all of the y values are the same on a horizontal line. Okay? We're going to quickly look here at the sum and difference properties now. Okay? All this means is the limit as x approaches c of f of x plus or minus g of x. That just means I can say the limit as x approaches c of f of x. I can find the first limit, and then I can add or subtract the limit as x approaches c of g of x. And what does it equal? Well, if I look in the top, the limit as x approaches c of f of x, they define to me as L, and the limit of g as x approaches c of g of x is m. That just means L plus m. I add the limit of each one together. It doesn't matter if I add them out here or if I add them in the middle. Okay? Product rule. The limit of a product is the product of the limits. So I can break this up. The limit as x approaches c of f of x times the limit as x approaches c of g of x equals, well, what was it? L times m. Okay? So, okay, great. I'm still really confused, Mr. Kruger. Would you please do an example to make sense out of all this? Oh, I would be happy to. Let's do a quick example here. And my example is going to be as follows. What is the limit as x approaches 2 of 5x squared plus 3x minus 4? Okay, well, what is it? Direct substitute in. What is it? Well, it's going to equal 5 times 2 squared plus 3 times 2 minus 4, right? Well, what is that? 2 squared is 4 times 5 is 20, plus 6 minus 4. Isn't that just going to equal 22? Okay? We could get nutty if we really wanted to get nutty with this. I don't want to, but I'm going to really quick. How the heck would all my properties of limits above this problem apply to this? Well, it would allow me to take everything apart and get the same thing. You're never going to do this. But what it means is really, I'll write this, limit x approaches 2 of 5 x squared plus 3x minus 4, okay? Understand this is 5 times x times x. So that just means I can take the limit as x approaches 2 of 5 times the limit as x approaches 2 of x times the limit as x approaches 2 of x plus the limit as x approaches 2 of 3 times the limit as x approaches 2 of x minus the limit as x approaches 2 of 4. Okay, great. Whoa, 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 whoa. I don't like that. Freaked out on me. Okay, so great. What does that mean? Well, here's the first one. The limit of a constant is the constant times the limit of the identity function, you plug it in, is 2 times the limit identity function, 2 plus the limit of the constant is the constant times, there's my identity function, 2 minus limit of the constant, it's the constant. What do I get? 20 plus 6 minus 4, 22. However, that was just a big fat waste of time to do it. That's why there's a thing called direct substitution. However, there are limits. We do need to remember how these properties work to take them apart, okay? So that gets to my quotient rule. Well, this is the limit as x approaches c of f of x divided by the limit as x approaches c of g of x, which is essentially just taking the limit of the top, which was L divided by M. That's what those limits equaled in the top, okay? The limit, the constant multiple rule. Well, I could have used the constant multiple rule before. Bottom line, that constant multiple, just like summations, if you remember, I can yank that little pot liquor out here and I can say the limit as x approaches c of k times f of x is the same as k times the limit as x approaches c of f of x, which is going to take me to k, that constant, times the limit of that function. Okay? K times L. I can just yank that little bugger out. And from there, we're just going to roll through a couple examples. Okay? So example, if, notice where these limits are all approaching. If this limit in number 1, if x were approaching 3, this data they're giving me up here means nothing to me, but the limit as x approaches 4 of f of x is 2, and the limit as x approaches 4 of g of x is negative 3. Find the limit as x approaches 4 of 2 times f of x. Well, that's just going to be 2 times this limit was 2, should be 4. Boom. Okay? When I look down here at number 2, the limit as x approaches 4 of f of x. That would be 2 minus 3 times, what's the limit as x approaches 4 of g of x? Negative 3. Well, that's going to give me 2 plus 9. This limit should be 11. Simple as that. What do I get over here for 3 and 4? Well, what's the limit as x approaches 4 of the opposite of f of x? Well, it's this limit as I approach 4 is 2, so the opposite of that is negative 2. That's like a negative 1 times the g of x is what? Negative 3. Negative 2 times 3 is 6. Okay? And over here, this is going to be 5 times. What's that limit as I go to 4 of f of x? It's 2 over the limit as x approaches 4 of g of x on the bottom. It's negative 3. It's going to be 10 over negative 3. And I can take that negative to the 10 to the 3 or just hitch it outside, and it works just fine. Hopefully you're following the sequence along here. Find the following limits by substitution. Use the properties. That doesn't mean peel them all apart like that big obnoxious one I did. It means substitution. Okay? Plug it in, Glade air freshen it. So that's going to be negative 2 squared plus 3 times negative 2 minus 5. Well, what does that give me? 4 minus 6 minus 5. What does that actually give me? Negative 7. Okay. What do I get for my next one? Ooh, a fraction. I don't like fractions. The limit as x approaches 3. Notice here, I'm just taking the limit. I'm going to substitute it in. So I have 2 times 3 squared over 3 plus 2. Well, 3 squared is 9 times 2 is 18 over 5. I cannot reduce that little rascal, so I'm done. Okay, I don't need to call it. What would that be? 3 3/5. I don't need to do that. I don't need to call it. What would that be? 3.6, I think. Okay. I like here. If I'm reduced, there's no common factors, top and bottom. I don't like to waste my time anymore. Okay, how's about here? As I approach 2 from the right, negative from the left, but I don't even need to worry about that for the time being. The only time I need to worry about that is if I get a 0 over 0. Well, I'm plugging in 2 minus 2 over, what do I get? 2 plus 2 equals 0 over 4. Whoa, what is a 0 divided by a number? That's right. It's 0. Okay? Is there any more underneath there? There's not. We're almost done. We got one more thing. I'd like you actually, it'd be pretty sweet if you paused it right now and tried 4, 5, 6, and 7 on your own. If I were a betting man, you're not going to get 7 right, but that's okay. You can try it. So here, when I'm coming in and I'm plugging in, well, check it out. I got 25 minus 25 over 15 minus 15 equals 0 over 0. This means work harder. That's all it means. Work harder. Okay. What do you mean work harder? That means follow your factoring skills. And I'm going to get rid of this so I don't run out of room. Well, what is x squared minus 25? Oh, that's really the limit as x approaches 5. I should write it out like this. I got x plus 5, x minus 5. How do I factor the bottom? Yeah, GCF. There's a greatest common factor of 3, x minus 5. Boom, boom, boom. Common factor. That's why I got 0 over 0. I can substitute that in. If I'm going to 5, I get 5 plus 5 over, you guessed it, tree. I guess that limit is 10/3. There's a hole. There is a hole in the function at 5, 10/3. The limit is 10/3, but 10/3 is not on the graph. It's kind of wacky and wonky, but that's the way it is. Okay? The point does not have to exist for that to happen. Okay? What are we going to do? We're going to plug it in, -3. So once I get into these, and now that we know this 0 over 0 thing, I'm going to plug it in here, and I get, -3 squared, I get 9. That's going to be minus 12 plus 3 over 9 minus 9. Oh, crap. 9 and 3 is 12. I get 0 over 0. Got another hole. And that hole is at -3, comma. We don't have to say where the hole is. We just want to know what the limit is, though. So I'm going to, because I don't want to run out of room. Okay, I always, did you hear me? I always direct substitute in the target point, the target value they want the limit for. You always plug it in. If you get 0 over 0, you got to factor that rat. X squared plus 4x. Ooh, looks like an x plus 3 times an x plus 1. X squared minus 9, difference of squares. X plus 3, x minus 3. I go bam, bam. Whoa, I was too fast. That means we're really looking at the limit as x approaches -3 of x plus 1 over x minus 3 equals -3 minus, or -3 plus 1. What do we get there? Or did I do something wonky and crazy there? I don't think so. I get -2 over -3 minus -6. I get You guessed it, a turd. Okay? A turd. So here I'm going to come to the next one. What did I say I always do? I always direct substitute in. So when I plug 2 in, 2 squared is going to give me 4 minus 6 minus 10 over 2 minus 2. That gives me what? That gives me negative 12 over 0. Whoa, that is not 0 over 0. That does not say work harder. That does not say waste your time. That says undefined does not exist. That limit does not exist. There is a vertical asymptote at x equals 2. I am not approaching a number. Okay? The very last one that we got here. I don't know if you remembered your logs or not, but when I direct substitute in 1 squared is 1, what is the ln of 1 divided by the ln of 1? And it's not 1. We have to evaluate. The natural log of 1 is 0. Natural log of 1. Work harder. How do I work harder on here? I don't know how to factor logs. Oh, you've forgotten your log properties now, haven't you? We're looking at the limit as x approaches 1 of, there's a little thing with logs that was called expand and condense. We had a power rule here. Boom! Numerator is really 2 times ln x over ln x. That's right. I have a common factor of ln x, which is actually going to equal the limit as x approaches 1 of 2. The limit of a constant is the constant. Woo! Pick the toothpicks out of your eyes. Get ready for tomorrow. Hopefully tomorrow's a little bit shorter, and then you will be ready for the whole entire bookwork for limits and the bookwork for 2.1 and the worksheet at 2.1. You can start it tonight, but you won't be able to do everything. But if you want to work at it, go for it. Talk to you tomorrow.